So welcome everyone, and today we're really excited to have Sebastian Griesbach share his work on exploring in diverse reward settings using a new method that he developed called temporal difference-error maximization, actually I think the method's called slightly differently, but that's sort of the focus of it. And Sebastian is a Ph.D. student at the University of Würzburg, and he's supervised by Carlo D'Eramo, and is working on deep exploration methods for reinforcement learning. And he also did some similar work to this at the University of Tübingen, where he specialized in machine learning and wrote his thesis on reinforcement learning at the Max Planck Institute for Intelligent Systems. And with that being said, I'll hand over to Sebastian, and I hope I didn't miss anything in the introduction. But yeah, looking forward to the talk.
Cool, thank you. Just quick check, first of all, do you just see my presentation or do you see both of my screens right now?
I see just your presentation.
That's great, okay. That's how it should be. Cool, all right, thank you. I'll jump straight into the topic with a quick motivational example. And you're probably all very familiar with this. It's a pendulum environment of gymnasium. Just as a very quick reminder, we basically have here as an observation just the angle towards the upwards position and the angular velocity, and our action is the torque force we can put on this pendulum. And in the regular environment, we have a reward function that is made up of different cost components. One of them just is basically the angle towards the upwards position squared. We have the angular velocity, and we have an action penalty for doing anything. Yeah, this is just a regular pendulum environment you probably all know. And if we throw soft actor critic on this, we get what we would expect. It very easily solves this environment. At the end of training, the policy looks something like this. So yeah, what you would expect, nothing hard here. But if we now take this environment and change it a little bit, and maybe we first think about, okay, what does this reward actually say? It says, well, point up, don't move, and don't put any force on the pendulum. And we can reformulate this objective in a bit of simpler way that still says the same thing, but let's do it differently. So instead, we now say, okay, you get +1 if you're pointing up somewhere in the upwards 5 degrees of pointing up, and also please don't do any actions, or like yeah, be efficient about what you do by applying an action cost. And here we would still have the same result that you should be pointing straight up, because if you're pointing not entirely straight up, then you always need to exert some force such that it would not go down again. So the objective is basically still entirely the same. We just rewrote it a little bit. Also, we make a little bit, also we change the initial state to be always the pendulum pointing down with the initial velocity of 0 as well. And now if we try to run this again with the same environment, just change reward function, we see that soft actor critic is basically not learning anything. And this is just one run, but you can do this many times. And if you take the default hyperparameters of SEC, you will almost every time get this result. This is what the policy looks at the end. It's a video, but it's just not moving because the action cost basically made it stop moving entirely. It's not like it's not learning anything at all, because there is this action cost. And if we zoom in on the y-axis, we can see, okay, it's actually learning to avoid the action cost, because, well, if you never see the sparse reward, then that's the optimal thing to do. And for the sake of the rest of my presentation, I now want to introduce this differentiation between the evaluation policy and the training policy. And we first do it with standard SEC. In standard SEC, during training, usually you have your stochastic policy where you get a mean and a standard deviation with a normal distribution usually, and then you sample an action from this distribution. Commonly during evaluation, you just take a deterministic action that's just the mean of this distribution. That's often done. So this is both the same training run. It's just that sometimes I look at the return of the evaluation, and the red line is the return of the training, and the blue line is the return of the evaluation. And what I want to show here is that the training policy actually starts out very actively. So it's moving around like this. It seems like it could at any moment actually find this sparse reward. But because it's only always encountering this action cost, it gets less active over time. So the more the training progresses, the less and less it's moving. And at the end, it's basically almost entirely inactive, and this will never find this reward here again. So the core problem that I want to show here is basically because the exploration gets stuck in the same local optima as the evaluation, we have a hard time finding this reformulated objective, even though the task itself is not any harder. It's just formulated in a way that's not as nice for our reinforcement learning settings. But the setting itself, I don't think is super unreasonable, because sometimes you just want to get somewhere and be efficient about it. And this is exactly the setting where you have a sparse reward and some action cost. So maybe we can just separate the exploration from the exploitation, such that these things don't get stuck in the same local optimum. And we just say, okay, our exploitation should just optimize the external reward, whatever this is. This is just some reward function given by the environment. And for our exploration objective, we say we take the absolute TD error of the value function of the exploitation objective. So this is just the external reward. This also means that this is still very much a task-specific exploration. This is not intrinsic motivation in a sense, because this still includes the reward of the actual environment. And we use the value function that we already learned for the exploitation, which also means that we kind of consider what we already know. Yeah, the general intuition here is that if you have a deterministic environment, it's very important that it's a deterministic environment, I'll get later to it, and you have a high TD error somewhere, then there's something to learn for you. So our exploration should seek these high TD error transitions such that our exploitation can learn from them and improve its value function. So if we now just do this in the naive way and say, during we use our exploration policy always during training, and we use our exploitation policy always during evaluation, then this unfortunately does not work. There's this nice paper from Scott Fujimoto where he showed that if you train two DDPG agents, exact same setting, exact same hyperparameters, exact same architecture, the only difference is one of them is allowed to interact with the environment and the other one is not. But they are both trained concurrently. So if one makes an action, then you get a new transition. Both of them are trained on this new transition at the same time from the replay buffer. It's really just that the thing is that we only one of them gets to behave in the environment, the behavior DDPG, and the other one only gets to learn from the same data. And we can see that the DDPG agent that is not allowed to interact with the environment, even though it's the same thing and has the same objective and everything, it's performing way worse. And in our case, it would be even worse, because our exploration and our exploitation agents don't even have the same objective, and they might also don't have the same architecture. At least they don't have to be. So to fix this, we do mix those two policies. The general idea is, okay, we have two policies. Let's just call them Pi1 and Pi2, and these can be our exploration and our exploitation policy, but they can be any arbitrary policies. Whenever you want to basically mix two policies, you could use this. And the general idea is that you have some selection mechanism where our behavior policy, mu, selects which of these two policies gets to choose an action now. And how we do that in detail is also not very difficult. It's first we select two candidate actions where we just ask Pi1 and Pi2, hey, what's the action that you would like to perform right now in this state? And then we calculate what I call the relative advantage. And the relative advantage basically just asks, hey, according to your objective, so Q1, how much better do you think your action is than the action of the other guy? But they are both according to Q1. And then we ask Q2, hey, how much better do you think your action is than the action of the other guy? But both according to their own objectives. And I'll get into the intuition for that right after, why this makes sense. And then we just take these two values, which are basically just two scalars, and do a Boltzmann distribution over them and choose the action according to that. So maybe a bit of intuition. Why does this make sense? Why does this help? Let's say we have here this a small state space. We start at S and we want to go to G. And in the state space, we can only ever move to the right. So we can maybe move up and down, but we have to move to the right, and we cannot go back. We cannot stand still. We have to move to the right. Now, if we have a policy that wants to go to G, well, it will go to G from S. But let's say we also have a second policy that wants to go to S prime, and we now do this mixing behavior as before, then we see that S prime is closer to S. So the relative advantage for policy pi should be bigger just due to the discounting, because we need less steps to get here. This is why this should dominate, and we will basically go to S prime. But once we have passed S prime, and we cannot go back, this policy 2 doesn't really care anymore what to do anymore, because basically it has reached its objective, and afterwards all the actions are kind of have no value to it. Therefore, this relative advantage will go to 0 for policy 2, and we will go back to G according to policy 1. And this is kind of the idea that this mixing can combine objectives of different policies with each other. I also have here some examples where I made it a little bit less nice. So we have two policies, one that wants to go here and one that wants to go here. And well, they can only go to one of them, and they will terminate once they go there, and also they're in different directions. And I just hard-coded these two policies and the according value functions for them. And then I made 4 rollouts, and these are the 4 trajectories when we do the mixing. And we can see that, well, they bounce around a little bit, but eventually they gravitate towards one of the goals, because once you get closer again, one of them will start dominating just due to the discounting. What we can also see if we look at where each of these policy is acting, so we can see the green upwards arrows is the policy wanting to go here, the orange downwards arrows is a policy wanting to be here. We can see that both of the policies are basically acting everywhere. And I think this is just an empirical thing, but I think this is really what enables this sort of mixing, enables both policies and both value functions to learn from the gathered data, because we're just mixing all the different spaces in the state space such that every policy acts everywhere, and they can learn from the data that they see. Cool. That's one of the problems maybe solved that we have, but there are also more. I call this a termination conflict of interest. Conflict of interest termination, I'm not sure if this is right. Let's think about the mountain car environment. You're probably also very familiar with this. And let's say our agent has not yet figured out that he needs to go to this goal. Then there is probably a very high TD error at this position here. Because if we don't know yet that we need to go there, then, well, the value function doesn't know that there's a high rewards, therefore there would be a high TD error to go there. Our idea is that we want to maximize the TD error with our exploration agent, but maybe there are also many other small TD errors somewhere else in the environment. And if we follow the regular formulation of the Bellman operator, which is this one, then we optimize for the accumulated discounted future reward. And maybe the sum of these small TD errors here is bigger than this big one here. And if we go here, we will terminate, so we can no longer get these small ones. So maybe our exploration agent would actually not want to go here, because it can get more TD errors when it bounces around just between these smaller things. So it would be nice if we have a formulation that is agnostic towards the length of the episode, because basically this will avoid termination, because there's only always positive absolute TD errors to get, because it's an absolute TD error. So instead of using this regular Bellman update, we use a maximum update. And what this essentially does is, instead of optimizing for the accumulated future return, it's optimizing for the single largest discounted future return. So if you think of, you have an episode, instead of summing these things up, you look for the single largest element in the episode. So the single largest TD error in the trajectory you can find, and you don't really care about what happens next. So in this case, if we look at this, and here, this is the largest TD error that we have, this would mean that our agent would go there and ignore everything else because it doesn't really care what happens after reaching this TD error. And then after reaching the TD error, of course, our exploitation agent would learn about this, and this would decrease. And so another one of these would become the largest one. And then maybe in the next episode, we go somewhere else, and so on. That is the second modification we made. And there's also a third problem that we addressed. That is that the TD error, of course, is non-stationary. So again, this is our reward function, which is just the absolute TD error. So the reward function for the exploration agent. And well, this includes the value function of the exploitation agent. And as the exploitation agent learns, this reward function will change. And usually, if we don't do anything about it, our exploration agent will have no idea why its reward function is changing all the time. So the idea is that we inform our exploration agent. Let's say this is our exploration value function, and this is our exploitation value function. And now maybe we can do some embeddings of our exploitation value function parameters, just to give it as an additional input to our exploration value function, such that if these things change, then our exploration value function, these words are way too close to each other, will be informed about it and can address this change. The actual embedding that we use is quite simple. It's a paper from Gene Harp. It's called fingerprinting, not the paper, but the method. And the idea is really just that we make up a bunch of probe states and probe actions. And these don't actually need to be actions or states. They just need to be vectors that have the correct size to be input into this network. And then the output, the answer, basically the Q values of these, are just our embedding. We just concatenate them to a vector, and this is now our embedding. And we get our estimate, which in our case would be the estimate of this maximum TD error. The nice thing about this is that if we now calculate a loss with this prediction, that we can backpropagate the loss all the way back to these probe states and probe actions, and during training adjust these such that they become hopefully more informative. Another way to write this as well is just, okay, this embedding is really just a bunch of Q values in a vector. Yeah, and we learn these states and actions over training. Putting all these things together, these three modifications, we get stable error-seeking exploration. That's what the method is called. And just to give, again, a quick overview. So during training rollouts, we use our behavior policy, where we do our policy mixing. And we now have an exploration objective. And this exploration objective has this maximum update, where this is the exploration reward and the discounted maximum future return. We have now a dedicated exploration value function, which has different parameters. And we use our conditioning, where we actually input the parameters of our exploitation value function as an additional input to our exploration value function. The exploitation objective is completely unchanged. This effectively operates at the same level as epsilon greedy. It's just that we have a whole different learning objective that influences how we choose our actions during the rollout. But the exploitation objective itself is only influenced by the data it receives during its update from the replay buffer. Other than that, it's completely untouched. So let's go back to our initial example of the pendulum. If you remember, this was the reward function. And now if we use sec with the addition of c, and we again do the separation between evaluation and training policy. Now here, evaluation again is just the exploitation policy in its deterministic form, and the training policy is this mixing of the two stochastic policies. We can see that at the beginning of training, our evaluation policy, you look in blue, evaluation rollout, is doing the same thing basically as the soft actor critic on its own. Because before you encounter this sparse reward, inactivity is just the optimal behavior. But our training policy actually is very active. And the point here is that it stays active. It does not get lost in the same local optima as the evaluation policy. And at the end of training, we can see that our evaluation is really nicely following up and is just doing this exact behavior of pointing straight down, even though the reward goes from here to here, because, well, if you're not straight down, you need to exert an action, which always gives you a cost. And our training policy at the end will also point down, but again, it just stays active and yeah, it's still moving around. And I think that is a nice exploration behavior. We tested this on 8 different environments with 3 different reward settings each. So the simplest one is a pendulum one I just showed you, but we also had a pretty hard one with the fetch, pick, and place, which was, I think, originally designed for the hindsight experience replay paper. And for each of these environments, we had 3 different reward settings. So the dense reward settings is what you usually have. So the original reward, for example, of pendulum. The sparse setting is where you just get a positive reward when you reach a specific goal, and the adverse setting, or the exploration adverse setting, is the exact setting that I just showed you with the pendulum. That is that you have a sparse reward and also an action cost on top. So in a sense, you're being punished for every exploration step that does not reach the goal. That's why I call it exploration adverse rewards. We use 2 different Bayes algorithms, soft data critic and TD3, and combine C with this exploration method on top of it to see if it can improve these things. And we found that in dense reward settings, it's not actually doing anything. Dense reward settings are very nice, and random jittering usually is completely sufficient. In sparse reward settings, it somewhat improves the rewards. And in these exploration adverse settings, it actually helped a lot. What is also very nice is that we did no hyperparameter tuning to do all of this. We essentially just took the tuned hyperparameters from the RL baseline zoo, stable baseline 3 zoo. There's an, I think it's, I forgot its name. I think it's RL baseline zoo. And just copy them over to our C editions without any tuning thing. So our agent basically has all the same our exploration agent has all the same hyperparameters as the exploitation agent. Yeah, but we just copied them and it worked, which is really nice. There's some plots here, and maybe I can just highlight a few things. So again, as I said, in the dense setting, it doesn't really do anything. We have here the full lines and the more darker colors is with the C addition, and the dotted lines, I mean the dashed lines with the brighter colors is a baseline. We can see in the dense settings, it doesn't really do much in most the cases. In sparse settings, it helps sometimes, for example here, but also here, actually, SEC seems to have a little bit better performance at the end. But in this exploration adverse setting, it seems to help quite a lot, actually. And I also want to maybe explain a little bit what exactly this SEC plus C is here. So SEC plus C means that we actually have 2 different SEC agents, and both of them still have their entropy bonus. So the exploitation agent also still have an entropy bonus, and the exploration agent also has an entropy bonus. And basically during the training rollouts, we sample from both of them and then do this mixing. But for the TD3 agent, we do it a little bit differently, because in TD3, usually you just put static noise on top of your deterministic action. And this doesn't really fit well with this idea of having dynamic exploration, because if you just always put static noise on top, regardless of where you are in the state space, this is kind of not the principle of this idea of having like smarter exploration. So what we do only for our edition TD3 plus C is that actually both the exploitation and the exploration are choosing the actions completely deterministically, and then just this Boltzmann distribution in the mixing is stochastic. But there's basically no random noise in TD3 plus C. In TD3, it's doing as it's always been done, with the static noise on top. But we can see that basically by doing deterministic exploration, we can in many cases perform better than TD3 with the noise, which I think is quite interesting to see. There are also the 4 remaining environments. It's not always working great. For example, in Hopper, actually regular SEC is being a little bit better. And what's also quite interesting is this fetch, pick, and place. It's both, all of them seem to be a little bit unstable, and only SEC can do anything here. But also seg plus c is the only method that is able to learn anything here really in the sparse and in the exploration at worst settings, which I think is pretty cool because it's really just a sparse reward when the box is at the correct position that you get +1. And only from the super sparse reward, it managed to learn to go to the thing, grab it, pick it up, and put it at the target position sometimes. It's not like it actually solves the environment. It only can do it if it's in a specific range and if the target position is not too far up in the air. But still, I think that's quite impressive that just using a sparse reward, it's able to learn anything in this pretty complex environment already. We also did some ablations to actually see what these 3 different modifications are doing that I presented. And here we grouped the environments by their different reward settings. It's only a subset of environments. And this is a normalization that assigns the value of 0 to the single worst one in a specific environment variant, and 1 to the best, 0 to the worst single run, and 1 to the best single run in a specific environment variant. And we can see with seg plus c, which contains all of these 3 modifications, it is actually here performing best. And we can also see that if we remove the mixing, that this has the largest impact. So mixing seems to be the most important addition. If we do the same ablation for TD3 plus C, it's actually not that clear. I think this has something to do with that it's super deterministic, and because it's so deterministic, it's also way more, it's way less robust towards different environments and towards different settings. But still, we can also see here that the mixing seems to be very important, but the maximum also actually seems to hurt in the sparse setting. Yeah, I think that's interesting as well. So I want to finish on some nice qualitative results that we have. One of the environments that we used is this half jitter environment with the exploration at worst rewards. This means specifically that the half jitter has to move 5 meters first before it gets any positive reward. And there's a threshold, and it also gets this action cost for moving at every point it moves. And now if we use seg plus c, again, we have this differentiation between the training and the evaluation run here again, that we can see that at the beginning of training, the evaluation does the same thing as the pendulum. Basically, it stands still, because before you have found the goal, standing still is just the optimal thing to do. And our training policy is doing whatever. It doesn't know what to do yet, but at least it's active, so it will eventually find the goal. And then at the end of training, we can see that the evaluation policy is really nicely jumping through the threshold. The threshold marks where the 5 meters are from where you get a positive reward. And it's just then standing still because it doesn't want to incur any further action cost. And now our training policy is doing something very interesting. It's also crossing the threshold, but then it's turning back. And it's basically starting to manipulate its body such that its center of mass is crossing the threshold over and over again. So it's really like it's trying to pinpoint where exactly this threshold is, because it's where the highest TD error is, exactly because there's just a jump in the reward function. And I think that's a really cool example to show that this is really nice exploration behavior as you would like it to see. And I think what's also nice, this is basically all the agent ever sees during training, because it's our training policy, and this is all the data that we can use to train. And still, we get this really nice evaluation behavior, even though we only get this really weird, messy training behavior here. So I think that's pretty cool. Of course, it's not perfect. There are things it can't deal with. I started at the beginning. It can't really deal with stochastic environments. If you think there's a transition with state action that leads to either +1 or -1 in the reward, then this will mean that the exploitation agent will eventually learn the mean, which is 0. And this means that the absolute TD error will always be 1. And this will never go away. And this could mean that the exploration agent gets stuck at this transition, basically going there over and over again. It's kind of similar to the noisy TV problem. It's not exactly the same because it depends on the reward function, but it's very related to that. So yeah, stochastic environments are still a problem right now. And another problem is super sparse environments like the Montezuma's Revenge. I used sparse environments in my experiments, but all these sparse environments do sometimes find a reward with random actions. But in environments where there's no chance to do that, the TD error will also just very quickly go to 0 because you always see, all you ever see is just zeros everywhere. So it also does not really deal well with these things. For my next project, I'm basically working on mitigating both of these issues, and the idea is to find something kind of a universal exploration strategy that should kind of work in most settings. Of course, it's not about being the optimal strategy, it's just about being a robust strategy that works most of the time. And the general idea how to do that is basically, instead of using the TD error, to use an epistemic uncertainty estimate, because then we don't have the problem with the stochasticity, and we can, if we formulate it right, it will also act in sort of as an intrinsic motivation in the super sparse environments. And with that, I'm done. The code is also freely available if you're interested in more of the details, or you can just also message me, of course, and now we can get to the questions. And thank you very much for your attention. And again, thank you a lot for inviting me.